Hello and welcome back to a new devlog here on the Ludwig Fusel channel. Now we are back in my currently empty solution here, or empty on the screen at least, solution from my web server development. And today I want to showcase you a bit of a new set of features that I have implemented. It's basically two things. First of all, I have written a bit of OS abstraction that I want to show because it kind of like comes together with what I want to mainly show. And what I want to mainly show is a job system, or I call it task system with tasks in a tasking folder. But in general, this is how you would implement a job system also for a game engine. Now, is it crazy to have such a job system for a game engine? I don't know. I've done a bit back and forward and had like a whole evening a discussion with a good old friend of mine who is doing a lot of consultants for myself recently. He's called Chat, so-called Chat GPT or Chat GPT if we want to pronounce this correctly. Now, I just queried a bit about with that, which is really nice, and it can push you forward to some information that you can then put onto Google and actually find the actual written statements that were kind of like coming from the ChatGPT opinions. And yeah, basically I've evaluated a bit, what is it worth doing a job system? Well, in general, it is a risk, especially for a web server. I mean, there is a reason why these modern coroutine APIs with stackless coroutines come into play. And how C# and so abstract them away from the user. In general, the idea of coroutines is to not have the stack switching at all, like a fiber, how you implement the job system in C++. Now, in general, like you can implement it, of course, also with threads, but the problem is with threads, you do not have into control how the scheduling works, and you need to rely on the operating system that it does correct scheduling, which in the end will not work out if you are on like a game engine that you need to have tasks switch around quickly during the lifetime of a frame. And thus you use fibers, which is basically same concept of a thread, but in end user mode, so in your application, and you can basically switch off stacks. It's not too difficult to actually do this. If you take a look on how CPUs work, you just need to store like the registers and restore some old register states, and that's basically what the fibers are doing. There's a bit more related on how this context work, which is why you still need a bit of the OS's help, and yeah, I wouldn't recommend implementing this on yourself in assembler. But the general idea is right. It works similar than a thread. You have like a stack, you have your own context of the CPU core, and you're switching these around, but you're not doing this via kernel transitions and waiting until the kernel schedules a thread. No, you do it on your own. You basically say, now switch context. And this makes it faster. However, there's a problem, especially on like web servers where you have a lot of I/O, and the main limiting factor is, in the end, probably, I can't really say if it will be the case, but probably is the I/O. So if you are waiting for data to be transmitted via a socket, or you wait to until the database gives you back a set of data, these are all operations that are kind of like I/O related. You kind of like put in you put kind of like a task, you kind of like assign the database a task, and then you're asynchronously polling, hey, has the database responded? And all of that is kind of like not something that indicates writing a classical job system like a game engine. Why did I still write that? Well, because I don't like the way on how coroutines look in C++. That's the main reason. Now, is that in the end gonna be a bad decision? I don't know. Currently, if I do the math, I can have 64 fibers per thread is what I have currently planned, and if I have this on a 8-core machine, in the end we have 512 concurrent calls that can be made. Now, if you would then measure in the worst case database response, you could come up with a number of like, if I would just like say we can it takes 1/10 of a second for a whole operation, which is actually quite slow. We would end up by still having like the capability of handling 5,120 connections per second. And I think that for now, this is going to be okay. If I in the end need to switch it, well, I need to switch it. If it's stackless, it would kind of like work that you kind of like put it on a list as well as I'm doing it here, but instead of kind of like fulfilling the list from like different threads and different fibers, you're basically working with a callback mechanism, right? You're going to put on work, and then the function will return. It will return back to the main function. The main function will circle around, grabbing new tasks, always going into the task. If the task completed, follow a callback that will then do additional work, and then at some point return back to the main thread, kind of like. However, this in the end is all like not a straightforward architecture if you're implementing this, and this is why I'm using fibers. If I use a fiber, I can do streamlined work. If I have a function, let's maybe I think I do have. Let's open up Notepad and hope that I can. This is something that I can show you. Now, in general, how this in the end would work is instead of having something like a class work, and the class work would have like a void start, then it would have like a void first IO done, then it would have a void send or first send done, and then it would have another void done, and you would need to implement all of your code in these multiple functions. What I want to have is I want to have a streamlined task function, like something like run or something like that, and I basically just say like read, which involves IO, then I'm doing my process, and then I'm gonna do my send, maybe an additional send. However, this might be implemented in the end. I want to have streamlined code, and this is what can happen with fibers, because read in the end, if I would go inside the contents of the read function, the read function would have kind of like a ASIO async read, and then at some point it would kind of like have a loop while not done. So while it does not receive the like kind of like async feedback from ASIO, while this is kind of like not done what ASIO shall do, I can now do something internally called fiber stall, which basically indicates that I have an IO stall, which is then gonna switch context to a new fiber lightweight thread, user mode thread, that then can continue in execution while this one is still like working in the background with ASIO. Then what I'm gonna have is I'm gonna have independent IO threads, like it's something that would even good fit to the P&E core architecture from Intel, but this is not available on servers, because on servers you always have like the performance cores. But yeah, in general, I'm going to have IO threads, and I'm going to have worker threads. The IO threads are just going to be serving ASIO, and I'm going to have additional IO as well. I'm going to probably write async file access IOs. I might write I'm not sure, but I'm going to write asynchronous I operation additionally to ASIO as well, which will be served by dedicated IO worker threads, and then the main processing threads will, with similar structures like that, kind of like wait until the IO threads are done. But that's not too much into what I want to show today. Today I want to kind of like show the architecture of the task system. You can see that there's quite a lot going on. This is by no means a full implementation. It, for example, currently lacks a prioritization of tasks. I might want to in the future have 3 priorities of tasks, like some very, very low priority auxiliary tasks that kind of like serve for example, if it would have this like webhooks, if I'm serving webhooks from the server, if I query other APIs from different subsystems, if some states occur, sending emails out, all of these like non-prioritized stuff will at the end kind of be like at the least prior tasks. And then I will also have a list of medium prior tasks, which would be like processing tasks that users await, but that are not like crucial for web operation. Like if I am doing like an async request to generate a PDF, I want to have the PDF ready as soon as possible, but it does not be like as fast as the API. It is allowed in the background to process that PDF, and then at some point kind of like tell the database, hey, the PDF has been processed, it is laying on that AWS bucket at that location. And then like the main threads, the most important threads, which are like for the connection handling, for the web connections, for having a fast API, they will then kind of like occupy the highest priority to react as soon as possible, because everything is at the end going to be a task in the end. Now, taking a look on how tasks look, I currently have an old architecture. This was also meant to maybe be implemented in the different way of having like a state machine and a main thread that goes like with the callback mechanism like SEO does it. And yeah, this is kind of like why these tasks look a bit not so straightforward. Basically, they have an init, run, and done as a virtual function, and according to these a few states. And basically, there's an execute function, and inside of the implementation, basically, I'm saying initializing init, running, run, finalizing, done, and then it's done. Now, this is kind of like super unuseful and super unintuitive. This is probably gonna change. I haven't changed it yet. This was like meant for the callback architecture, right? You would have an init function that would be instantly called when a new task is scheduled. So if you are kind of like saying, all right, I want to start an IO operation, this init function would be instantly be executed, which would basically kind of like place the ASIO IO request. Then what would be happen is that there would be the run function, which would be kind of like called every time the task is kind of like served from the list. And this run function would kind of like poll the ASIO state, and if it is finished, it would kind of like say, all right, I am done, I return true, or no, I'm not finished, I return false, and if it's false, it will be re-enqueued, 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 and at some point it returns true, and then the done function is called by the kind of like task system to then kind of like follow callbacks and stuff like that. But this architecture is gone now. I might implement this in the future as well if I need it, or change the whole task system, which I would not like to do because I have like spent like 3 days now on that thing. Was kind of frustrating. I just like one evening where I was sitting and just writing 5 lines of code, seeing no, this is not how it should be. Talking with ChatGPT, starting approaches with like coroutines, starting approaches with a fiber system, starting approaches with the state machines and callback architecture, completely questioning if I even shall write this whole web server and stuff like that. But that is already over the point. This web server is going to exist. But yeah, still you're going to have this these like core questions as well if you are on a complicated development like that is of a job system. Especially if you don't know how in the end it's going to be. I hope that the fiber system performs well. I think it performs well for a game engine, but still a game engine is not that I/O. It's like computational intense, and this is what everybody tells you. If it's computational intense, use fibers. If it is I/O intense, maybe use something differently. So I'm actually doing something against advisors out of, already explained reasons. I hope this is going to go well, like my Mars tells that, but yeah. In the end, it's also a question on how it's going to end up. Another thing is memory consumption, right? The fiber has its own stack. So in Windows, it's 1 megabyte to standard size, which makes sense, but can be tuned for the application, of course. If you have 64 per thread and you have a 32-core server, you're going to end up with having like just 2 gigabytes of memory just for the stacks. And of course, if you have a 32-core server, chances are really high that you get like 16 gig of memory. And if you have Linux, which this currently does not run on, but this is a different story that we're going to get to, it's not going to be too much of an issue, right? Because you don't have like too much OS overhead. If I like say 16 gigabytes and I like say, all right, let's be like Linux doesn't need that much. But if I just say out of good means, I'm just dedicating 2 gigabytes for the operating system and for like people that might go in and run Python scripts that administrate the server, that need to do something on the server. I'm still like left with 14 gigabytes. Then there are like 2 gigabytes for a stack, which leaves the application like left with 12 gigabytes of RAM, which is definitely enough. If I'm taking everything here later on, there are going to be a few more gigabytes wasted on like allocators that just idle around and keep memory there for being fast. In the end, this thing will eat a lot of RAM, of memory. But I think it's going to be fine. But we're going to see. So this is the nice thing. This is C++. If the architecture in the end doesn't fit, and we can basically just adapt that. That's a nice thing if you control both. If you're controlling, not both, but everything. I control everything that runs on the server, at least not the operating system. But except of the operating system, I'm controlling everything. I'm controlling the web server, I'm controlling the framework, I'm controlling the app. So I can do and tinker around with everything to optimize it so that it works for the use case. But yeah, this was like the longest talking for like 2 files of code that are not long. Let's talk about how this all works. Now, in general, what we do is we need worker thread, right? This is the most primitive that we need, that we always need, no matter on which architecture we would go for. What we need are worker threads, so real threads that interact with the operating system. How to interact with the operating system? Well, I'm using something called API thread T and API thread ITT, so thread ID and the thread. Now this API is something that I've written on my own. It's the OS API is how I've called it. The OS API currently has system.h, which can do a bit of system discovery, like logical core count, physical core count, ENP core architecture for like Intel 12th gen, because actually, this is also something I thought about, since I have now a 12th gen machine. And I have like the ENP core architecture, and I was already thinking when I've initially bought the CPU at the mainboard, which is actually quite a while back. I think I had it like 1 year just sitting around. It did not build the computer because of some reasons, that the components were not fitting, and I thought about building a dev machine that I'm just using for software development, and one that I use for gaming, and have like my AMD gaming rig and then my Intel development rig. And now this completely changed. My old AMD rig will at some point, when I find the time, be transformed into a server, a big server. I might want to then use Nutanix on that server, which might be also quite a journey for us all to go through. I might can do some videos on these. But that's not the whole story, right? The idea was to do a bit of optimizations and programming for 12th gen. I found out that 12th gen on servers isn't that big of a thing, but in general, yeah, it's we're not going to go into that one. But that's just some side stuff that I shouldn't even talk about. Now, what I talk about is the API for threading. Basically, what I've implemented myself is a set of API rules that every operating system must fulfill to be compatible with my architecture. This is even a bit deprecated, because I'm using thread local storage and fiber local storage, which is not used currently at all, because I'm using some my own abstractions on top of that, because I also found out that fibers on Linux are actually not an easy thing like they are on Windows. Fibers, like these lightweight user mode threads on Windows, they are an API set. This is an API from that's delivered by Windows. The functions look very similar on how they look to threads, and basically you can just use fibers out of the box. This is not how it works on Linux. On Linux, there is something, I've already forgotten how it's called, but there is like this context API. Linux fibers, oh my. Is this dude already, is that dude liking them, or is the dude not liking them? I don't know, but in general, consideration implementing. Come on. I do want to just find that one single keyword. Signals? No. It doesn't work. If you want to find something, you're not gonna find it. There are, however, these I do need to ask, consider my ChatGPT chat, because he told me. Coroutines introduction. Make context. Yeah, get context, switch context, swap context, and make context. This is how the API sets are called on Linux. Swap context. This is basically the function, the POSIX function. It's called user context, and you can make the contexts and swap this context. And these are basically more or less fibers, but with a bit more work around than they are on Linux. Again, I'm not too much into Linux programming at all. Currently, I have just used like the standard library and cross-platform libraries on Linux, and in the end it worked. I do had for a project once written abstraction layers between Windows and Linux, and in general it's not even too hard to write these layers. In general, I just have two libraries, one for POSIX based system and one for Windows based systems. If you take a look at the Windows based system, you can see how it works behind the scenes for Windows, redeclaration of the API, and then a bit of an implementation. In general, I do not want to go too much into the details on all of these functions work, but I just want to show you how this works. In the end, these are fibers. These are all gonna be reproducible on one or another system. In general, I have a bit of thread init and thread shutdown, which is initializing these subsystems, was mainly used for thread local storage, which is no longer being used. So these functions in the end will be deleted as soon as I really see that I don't need them. Maybe I need them on Linux, then I'm gonna go back on actually using them, especially for the constructs that work on Windows but not on Linux. I might need to use thread local storage to kind of like mimic fiber local storage, or what I currently use as fiber local storage on Linux, maybe, but I cannot really tell you if this needs to be done. But in general, what I can do is I can interact with thread and fiber local storage, basically getting and storing the pointer on a pair thread or fiber based. Then I have the opportunity to set the fiber and threads stack size. I want to later on expose this as a config option to the server itself, so that you can actually tune this on a per application base to say how big you want to have your stack. And of course, if the stack overflows occurs, then we need to also catch this later, which I need to still see that I implement this. However, then what I have is that I can create threads. I can assign a thread to a core, which basically sets the affinity of a thread. So creating a thread with a main function and retrieving its ID, assigning it to a core so that it will be only run on that core, which basically is a good idea, especially if you are running on a multi-core system, right? You can see all of these are my cores. If every thread is like working on one core, I can take the most out of the CPU without like needing to rely on operating system. It's commonly used in games actually. Sometimes if you're, especially during level load of a game, if you're opening up the task manager while the game is loading data, you'll see all your threads going up to the maximum, because they are doing like all the processing. They are doing taking what's kind of like stored on disk. They are copying it to the CPU, they are decompressing it, maybe de-encrypting it if the package is encrypted. They are making sure to translate the static data that's on disk and bring it in a runtime format that can actually be run on the engine. And then at some point you see like all of the cores like whew, going down again, and then just a few running like the game, because nowadays we are not CPU bound on games anymore. Of course, with like things like AI, and actually at some point these days it's even more interesting to put some of your work in a game to the CPU than to actually to the GPU. For example, what I have thought about when all of this ray tracing stuff came out, I had the idea of, hey, maybe it's possible to implement audio on the GPU, which is kind of like a bit weird. However, if you look at if you're thinking about that, right, the idea would not be to actually do like the audio processing on the GPU. The idea would more be to kind of like find coefficients for your audio pipeline. You have like 3D objects in the scene. You have a very simplified model of the scene on the GPU. You ray trace across the scene from the audio listener to actually, or not actually from the listener, actually from the audio source, and see if the audio of array of the audio source hits the listener or the other way around. It depends on how you would want to implement that. And based on these computations, you could kind of like compute how loud audio sources would need to be. In general, it would be a bit harder to do these because you would need to make sure that the rays actually hit these things, but I was thinking about that, but then I was also thinking about, right, on the GPU, there's so much rendering work. Why would you even want to put audio on the GPU? It's not a good idea, right? Even if it's just for finding coefficients that are then feed into the real-time audio pipeline on the CPU. But it would be an interesting challenge to write. But that's not the topic of today's video. Just like, I love how I can go from like, this could be a paradigm, right? It's a paradigm how I can bring every non-gaming related programming task to a gaming related one. But yeah, we don't need it yet. Like, okay, what we can do is we can assign a thread to a core, and what we can do is we can create a fiber. Now, what a fiber is basically, it's just a pointer to its control block. In my case, it is a fiber T, which is a void pointer. On Windows, it's basically a struct that then holds the pointer to the fiber control block associated with the metadata, but that's a different story. Basically, the general idea is this is a kind of like handle to the fiber that you can use to kind of like tell a thread to no longer process what it's currently doing and switching to the stack and the state of this other fiber, which also, of course, starts at the main function. Now, what I also do is I have an additional void pointer for a context. This context is used to kind of like describe the state of the fiber. You can later see what it's doing. Basically, this is a pointer to a so-called fiber context that I have defined here. We're going to go through that in a second so that you can actually understand on what's going on. Now, what I do have is a few helpers like resuming a thread, basically creating a thread since I want to move them to a different core, is creating them in a suspended state, which basically means that they are not executing the threads. They are kind of like idling around, not doing anything, and Windows is not even considering running that main function until I call thread resume, which gives me the time to assign it to a core and then call thread resume, so it directly starts on that core. Just a bit of stuff that I know from Windows. I hope that there's a Linux equivalent. I haven't taken a look at this. But there will be a way to do it on Linux as well. And if not, then the function will just not do anything and it just will be an empty body. In the end, it will still work because the operating system will do the scheduling and setting it to the right core. And in the end, it would probably work also, maybe not as well as on Windows, but Windows might have other drawbacks why it's not suited for a web server. But it might be actually, like all of this corporate stuff is at some point even still running Windows, which I know from professional experience of working on automation technology for the process industries. So yeah. Yeah, I can create a fiber, and then I have these like utility functions, and then there is a very interesting set of two functions. These are the thread convert functions. There's a TTF and a FTT conversion. TTF means thread to fiber. So if you're calling that function, a thread is converted to a fiber. Basically, what this means is that there's a new fiber created, and it's kind of like plugged into the context of the thread. So there's a fiber converter created. The thread is kind of like adjusted to that fiber, and then will run that fiber. So in general, that works the same like creating a fiber, instead that we don't need the main function, because basically the thread will continue where it is, but no longer as a thread, but as a fiber. And so we are kind of like getting a fiber pointer to get a context to the fiber. And we are also, of course, needing a context internally for our own state management. The other way around works as well. It's important these needs to be come together. Like if thread number 5 converts to fiber number 6, fibers number 6 must be used on thread number 5 to convert back to a thread, which is never mentioned at any like API, which had given me like, let's say like 20 minutes, 30 minutes of a headache. I had implemented something that only like the so-called, I named them root fibers, so the fibers that were originating from a thread. I have implemented a mechanism that only root fibers will convert back. However, I had not implemented that it needs to like convert on the same thread ID, which was like 2 lines of code more. And then I made a mistake in my statement and had like an and instead of an or, and then it was like screwed up again. And I was not even sure if this is the reason why it's bad. And I went trying to debug some other stuff. It didn't work. And then I saw, all right, there's something wrong here. Let's change it, and boom, yeah, it worked. I don't know why it is. Maybe if I have time and still remember later, I might do a pull request on the Microsoft Docs to add like the description of that thing to the docs as well. Would not be the first time fixing the Microsoft Docs, but yeah, it would be a good idea. Next thing is getting the fibers context. I actually have a function that can give me the current fibers context. This is required since I'm not always going to have access to the context. The actual fiber scheduler will always have the context of the fiber that's currently in like code execution. However, as soon as we are kind of like going into the job, that context is lost because it's not passed on to the job. And if the job kind of like has a stall, then we need to kind of like get the context. This is why I've implemented that. This only works for the current fibers and only if we are a fiber. I also have this function again for a fiber pointer. So if this is kind of like for the current fiber and this is for any fiber, which works because I store the context in this fiber T on Windows. Now, what I also have is I have a way to get the current fiber running on a thread. I also have the function to let's maybe talk about these as individually. Now, get current fiber just basically checks what fiber is running on the thread and returning that. Quite simple, actually. Now, this one is a bit more involved. Thread switch to fiber. What basically this function is doing is this function is now changing execution context. So you're supplying a new fiber. Basically, what this means, the function or the caller of that function here is going to be suspended. It's going to be suspended. The thread is no longer executing that current execution context, that fiber. Instead, it's going to taking the execution context of this fiber and puts that on execution. And this is very important. If this function returns, it means that the caller, so the thread that was paused in favor of that fiber, or the fiber that was paused in favor of that fiber, is has now been switched back by another call to this function, but from a different fiber. So if fiber A calls this with fiber B, fiber A will at some point, if this function returns, continue its operation because some other fiber, for example fiber B, or even a whole different fiber on a whole different thread like fiber XYZ. If fiber XYZ calls this with fiber A will continue executing. So this is actually something that's a context switch. This is a bit hard to kind of like understand and get if you're not used to the concept of like fibers and scheduling. It's not that you're calling this function and then the function returns and you have the new context. No, you are going to block until, or the fiber that calls that, the caller is going to be blocked until the caller is explicitly activated again. It's important. We're going to see later why it's important to understand it, but it's like a main catch that you need to get when you're working with fibers. If you call that, and the call returns, it means that somebody else has wakened you up. Especially with fibers. With thread, it doesn't work like that, because with threads, it's the operating system. The operating system will, if you are kind of like switching to a different thread by calling yield or sleep or any of these thread-related functions, if you're calling this, you will be awakened, definitely, because operating system will do it. Only if you're doing something like wait for single object on Windows, and the object is never kind of like Z, and you are waiting for an infinite amount of time, your thread is not going to wake up again. But in general, if you are doing like what the thread-related stuff, the operating system will awake you. It's not with this on a fiber. Fibers needs to be explicitly awakened by the application itself. And this is why you need to be really careful to handle fibers correctly. Because a fiber can only be switched to if it has been completely pushed away. And if you're reactivating them previously, you can get it with like race conditions and memory leaks. So basically what you need to do is a fiber needs to make sure it puts itself on a queue, but it needs to be also sure that it does not put itself on a queue before the thread switch to fiber has returned. But if this function has returned, it has already been reactivated, if that makes sense, which is kind of like a paradigm which you need to get around. You can see how we get around with that. Basically, we are doing some messaging. We are telling the fiber that we are going to activate. We're basically telling this fiber that the first action this fiber shall do shall kind of like queue the old fiber back on the list. That's what we're gonna do in the end, or on the queue actually. But I'm gonna get to this like later, but this is like a very important function, thread switch to fiber. Then I have a bit of informational function again. If a thread actually runs a fiber, it returns true or false depending if it is currently executing a fiber, and it also has an option to supply kind of like a pointer to the fiber that's actually running. Then we have a few destroy functions, and that's basically it. And this is implemented for Windows. Actually, if you're taking a look at the implementation, it's not too bad. It's like 200 lines of code with a bit of stuff around that, like having like a fiber main, a thread main that then actually calls the real main functions, having a bit of this TLS stuff that's deprecated and gonna get away here soon. Then like storing internal stuff, allocating new objects with our default allocator, creating an actual thread, making sure that it is created in the right state, that data is passed on to the thread, that the structures are actually correct, right? Like we have this configuration here with like the stack size and fiber local storage. Then we have the thread data, which is like the window thread handle and the thread main. We have the fiber data with its context, the main function and the handler. So basically this is our thread local storage. This is why I don't need them, because I have these structs that are passed to the thread, and these are actually the handles. A thread handle is actually a block of memory of that struct, which is why I don't need fiber local storage and thread local storage, because fiber local storage is the context and the thread doesn't need one currently. There is a lot of stuff going on behind the scenes, but in the end it's just a bit of wrapper around the Windows API, which is not too complicated actually. Like, just read the docs, call these functions, make sure that your structs are in the right integrity, that they are created and destroyed when it's required. For example, if you are converting to a fiber, you of course need to have a new fiber data struct. You need to wrap the context in here. You need to assign the handler, and also kind of like convert the thread to fiber, provide this to the internal one. And doing like all of these stuff that is kind of like happening under the hood, and making sure that your data is not getting lost, you're not getting any memory leaks. But this is also why I have my own internal allocators, because initially I had some memory leaks and my allocator was screaming at me, yeah, you have memory leaks, you should not have them, they should have been freed by now. And then I can like go in and see where the actual memory leaks are. And basically, it's just a bit of a wrapper around the Windows API. It's going to be a bit of work to get this done on Linux, but with these context switching APIs, it's going to be a bit more. It's going to be a bit longer. I like think it's probably going to be double the size than on Windows, but in the end, it's going to work out. Now let's actually talk about the real things that happen, like the worker thread. We were just at the first class of worker thread. Now, what is the worker thread? Basically, the worker thread is just a usage of these APIs, right? We are creating a thread, we are assigning it to a core, we are resuming it, that it will at some point go inside of the thread main, which, yeah, basically, I do use thread local storage. Interesting. I don't think that I use it as somewhere else, but it seems like I do it at some point. I think this is deprecated that I can remove. But yeah, currently I'm using thread local storage somehow. So yeah, basically what the thread does is, since everything in our system works with fibers, the first thing a thread does after it said hello, it will basically convert itself to a fiber, and it will use something internally called mfiber data that's actually supplied with the constructor. So I basically already tell a thread during creation what data shall be assigned to its fiber, which is basically the fiber context that's managed externally. And yeah, then I just call something called fiber main, which is my good old main function for fiber. This is a floating function, actually. There is something called a fiber main here. Basically, the fiber main is a forwarder that actually calls the fiber main forwarder, and the fiber main forwarder is an SD function with an int return value that's by default doing nothing, but of course, since it's static in here, kind of like a singleton, it's possible to get it and set this one, which basically makes all of these object-orientated stuff boil down to one only fiber main in the whole application, which is the whole point of a task system. So we are kind of like mix and matching OOP programming with non-OOP programming, which is something you should not be too scared of, but you need to make sure that everything is handled correctly. Of course, you need to wrap your head around that. I'm doing a bit of stuff with also if the fiber has returned, the thread has returned. I had initially a few issues that required a bit of more synchronization, so yeah, that's why this is here. Yeah, so that's basically how worker thread works. Basically, it's just a wrapper on how do I kind of like beat a thread down so that it is behaving exactly like my fibers shall behave. In the end, everything boils down to calling this like fiber main, which is going to go to the fiber main forwarder, which is at some point going to go into the so-called fiber scheduler. Now, this is my glorified big-ass class that handles everything, including like concurrency and stuff, with queues, task queues, fiber queues, but we're going to get to the theory of operations soon. Now, in general, there is somewhere something called fiber call. This is basically the fiber main. Every fiber will at some point call the fiber call. And this is my main then. Now, we talked about these fiber contexts. To understand the fiber scheduler, we need to take a look at the fiber context, actually. Now, the fiber context is quite simple. We have a scheduler that is owning the fiber. This is always going to be one, but I do store them in here. I can get rid of this if I have implemented. Currently, there's no singleton of the fiber scheduler. As soon as this is the point, I might throw that one out, because it's just increasing memory usage. But basically, yeah, it kind of like has the owner of the fiber in here. It has a reference to the actual fiber pointer, to the sys fiber. It has a fiber ID stored in here, which should actually be an API fiber ID. No, not. It is not an API. The thread IDs are unified, but fiber IDs are actually a size T and the construct that I have come up. These are actually fiber IDs are just a virtual thing. Actually, fibers are identified by a pointer to its control struct. As I already told you, there is nothing like an ID. This is something that I have implemented. Then what I store is I'm storing a bit of information about the root fibers. Root fibers are going to be fibers that are called by a thread. So a root fiber, yeah, it's going to be basically assigned true if it is like owned by a thread. And if this is the case, it also stores the thread ID. This is required to later on synchronize the root fibers to their owning threads to make sure they are cleaned up by the right thread. Now, after that down here, the carnage begins. Or actually, this is like the peak carnage of the whole job system. It's the so-called fiber activator. And this is the mechanism to make sure that if a fiber gets activated or switched to, that it makes sure to kind of like finalize the previous fiber. So what we are storing is the context of the previous fiber. So fiber context, previous context. So this was kind of like the fiber that called switch to fiber. And basically what we are doing is we are feeding this activator with this previous context. And this activator is a function pointer to any void function that takes two fiber contexts. And it's actually not now, it's actually now and previous. I've changed it somewhere else, but it seems like I've not changed it here. So it's kind of like giving the current fiber context and the previous fiber context to that activator. And then this activator can make sure that like the old fiber is put on the right queue. This is basically why it's a function pointer, because there are two options actually. There are a so-called fiber pool and a fiber queue. Fiber queue is for all fibers that are not finished, and the fiber pool is for kind of like all open fibers that have finished work and would need a new workload. Speaking about workload, the workload is basically a task pointer inside the fiber. Now, how does it all come together? Well, it all comes together in the fiber scheduler under the usage of the fiber pool and the fiber context manager. Let's start simple. The fiber context manager is basically just an STD vector around all of my fiber contexts. So basically, it's just a container containing all of the fibers, and I have a bit of indexing going on here, which allows it to index fibers. My root fibers are basically stored at the slot 0 to n, and all other ones are like stored from on like not 0 to n, 0 to n minus 1, and all other fibers are stored from n to n minus 1. And basically what I'm doing is I'm basically telling this context how many threads I have and how much total fibers I have, and then this one can do the correct offsetting to make sure that it can give you context for thread fibers, so fibers that are like core fibers. Back then the name core fiber was not existing. All right, there is root fiber. Get context for, we can do a quick rename here. Since I have Visual Assist now installed again, I can do a quick refactor to make sure this is now called root fiber. So I can get a context for a root fiber and for a normal fiber, and a like non-biased, just give me all context functions. Even though that one is the same then in general for the root fiber. Now there's no safeguards in here, it's just a dump container. The fiber pool, on the other hand, is a bit more intelligent because this one is actually managing fibers. The fiber pool is actually creating fibers using the thread create fiber and the reference to a fiber main as well as fiber data. Fiber data can also be retrieved with a function. So a lambda or just any STD function that gives a void pointer for a index, and this one is later on used to kind of like give it the right fiber index coming from the fiber scheduler. So the fiber scheduler is going to manage the context manager, and then this kind of like fiber data factory function is kind of like accessing the fiber context manager to get the right context for the right fiber index in this case. Now, in general, the fiber pool is also cleaning up the fiber, so it's actually going to go through all fibers and cleaning up all fibers. So even through the fiber pool, this one is actually asserting it. The fiber pool is actually a container. It's actually a ring buffer. It is a ring buffer used as a queue, where I can get a next fiber and I can return a fiber. Basically, it's a ring buffer. It's an implemented ring buffer with non-atomics. It's completely locked, but it's locked with a spin lock. So we are not having a mutex that is like going back to the operating system. It's just a spin lock. It will basically, as the name suggests, spin around doing nothing, just like do. Okay, it's a nice imitation, but it's basically it's just idling around until kind of like the critical section is released, and then it will go in and go down here using atomics. And yeah, this is kind of like the idea on how this works. It's just it is a DQ, but with a ring buffer. I've implemented this previously. I could also have used the DQ here, but I've implemented this as a ring buffer, which might perform a bit better than a DQ, but I'm not sure of that. Maybe pointer arithmetics would be a better choice, but yeah, maybe it can change in the future, of course. Now let's talk about the actual thing where the magic happens, the fiber scheduler. let's actually walk you through how this fiber scheduler works, starting at the constructor. Basically, what the constructor is doing, it's initializing a few things. Don't bother what's going on here. It's just initializing the containers and bit mass of total fibers and thread count. Basically, what I am doing is I'm forwarding this, the fiber main forwarder. This is like the static instance for the main function. I'm basically binding my fiber call function to this instance, which is a very simple call here. And after I've bound that fiber call, which we're going to have on later, I'm going to go in and create my fiber context manager. I'm using this with std make unique. I don't think that make unique would be required here. I might in the future change this to be like a static instance on the class, because the fiber context manager is not as involved as it was initially planned, or as it was at some point during development, but the fiber pool actually is. The fiber pool is a bit more involved. We need std make unique here. And by the way, as I told you, CVP std is basically std. It's just a bit of magic of my own allocators. Don't really need to understand this for the concept of the job system here. Now, basically, what I am doing here is I'm creating a fiber pool. I'm telling the fiber pool that the fiber main is the main function, so I'm not directly referring to my fiber call. I'm always referring to fiber main, which is redirected to fiber call. And then what I'm doing in here is I'm providing a lambda for the fiber data. So I'm providing an index. The index is iterated, and then I'm going to get the context for the actual fiber, not the thread fiber, the non-root fibers. And the fiber context manager is making sure that they are giving me the right contexts, and I'm basically providing the data so that every fiber gets its unique context. I have a bit of math on how this works. So basically the fiber pool is going to hold as many fibers as we have in the application minus the number of threads, because we're always going to have fibers that are running on a thread. So the fiber pool requires the number of fibers less than we have threads. This is basically just implemented here, and it also gets an allocator. After that, I create my worker threads. I'm basically iterating through my thread count, and I am creating worker threads. I have my allocator in here and the context manager, and now I'm getting the context for a root fiber, and I'm currently putting them on course 0 to n. Of course, this at some point, because this is like a magic number currently, even though it's not, but it's like 0 to n minus 1, but in the end, it shall be configurable, that you can tell which course shall do the work. If this is going to be like might be a core mask. I'm not sure how I'm going to implement this, or if I'm implementing this on a core base, that I basically have a configuration file for each core, and I kind of like tell it the role of the core, and in the end this is going to abstract away in like a vector initializer list or something, probably a vector, not an initializer list, but like a vector that tells for like each worker thread which fiber it's going to go in. There's some translation and configuration going on, but configuration is not a thing on this project yet. So this is basically how the workers are created, and as soon as the worker is created, it will also be started, which means that it will like go in here, and it will convert itself to a fiber, and then also call a fiber main, which means that it will also at some point, the same then like the fibers, as soon as they are activated, call the redirected fiber call function, bound function, that's going to be somewhere down here. So what we now have is we have a uniform way on all our fibers. They will call the fiber call at some point. So this is basically our main function down here. After like a Windows main function, after a main function that's then redirecting to another function. So there's a bit of abstraction going on here. We do have a bit of shutdown in here. The first thing that I do is I'm calling a so-called shutdown function, which is actually just going to set a Boolean. It's just going to set a Boolean to false, which is called keep running. So as soon as we shut down, we shall no longer keep running, and then we basically have a while true loop. And basically what we are doing is we are iterating through all of our workers, and as soon as a worker has not returned, this worker's alive goes to true. And as if this is true, it will basically sleep 100 milliseconds and will try again. And as soon as there's no worker alive, it will break out, and then it will clear the actual worker, which will destroy them, which requires them to be shut down. So basically this is how the rollback of the class works, and everything else can then happen automatically. Now, how does the fiber main work? So the fiber main is actually a bit more involved. The first thing that happens is that I'm gaining access to my fiber context. Basically thread get fiber context, then I have it. Then internally I can set up a few things. First of all, I'm setting this fiber pointer, and then I'm going to set the owner. After that, I'm going to check if it is a root fiber. This is actually something that happens. I think we have skipped that one. Here, init fiber context function, we have skipped that one. That is actually initializing the fiber context. I'm basically assigning the fiber ID to a value of I. And for all of the root fibers, it's basically setting the root fiber value to true so that we know that they are root fiber. And if we are knowing that they are root fibers, basically what I can do now is I can assign the thread that was initially like calling the root fiber. So now I have the reference that I can later use to kind of like restore the correct thread attribute so that the correct thread is converting back the fiber to a thread with the right fiber so that everything is correct. Then I'm just going to add a hello from fiber because now basically fiber has initialized and it says hello. Now the next thing that happens is quite unusual. There's something happening called fiber reactivate exec, which basically means execute reactivation. As soon as a fiber is reactivated, I told you that it might needs to do some enqueuing of the data of the other fiber that has activated this fiber. Now this has only the chance to run once, and it will in the most cases not even do something. Or actually, yeah, for the initial fibers it will do nothing, but later on it will always do something. Basically, on the first fiber call, which means that the fiber is initialized, the fiber kind of like initializes itself and enters the scope block, it still needs to make sure that it does cleanup. Even though it has not done a context switch on its own, it still needs to do cleanup because it was switched to. This function is as robust if there's no like thing going on for this fiber, then it's not an issue. It will do nothing. After that, we are going to go into our big ass main loop. This main loop is basically running or having a few conditions in here when it shall run. Of course, as soon as our application has no shutdown condition, it shall keep running. As soon as we have a shutdown condition, we need to make sure that we are doing cleanup. So first of all, I must see that our task queue is empty. As long as we have something in here, continue the while loop. Same goes for our fibers. So all like idle fibers that were blocked and had a fiber stall, they need to kind of like also be empty. We don't need to have fibers in the queue that are waiting execution. So this is important. And what's also important is that the fiber has a chance to also do its own work that is currently being tasked to do. So as soon as we have work, or there's something in the queue, or the application still keeps running, we are going into the while loop. Now, what are we doing in the while loop? The first thing that we are going to do is we're going to check if we have work. So if we have work, well, good, do it. If we have not any work, we basically need work. Fiber need work. It's a very simple function. It is basically just locking the task queue, checking if it is not empty. If it is not empty, it's going to get the front and put it in the own work slot, and then it's going to pop from the front, and then it's returning true. So basically, it's supplying new work to a task, to a fiber. So a fiber has a chance to supply itself new work even though nobody else assigned it work, which does happen. If a fiber finished its own work, it can either go back on the pool and later on be reactivated by a different fiber and already been supplied with work, or it can be kind of like self-reactivating itself with work. Then I have a very rudimental execution of work. So I'm going to run the execute function and setting the work to a null pointer. So the work is not managed currently internally. This might be a shared pointer later. I'm not sure if I want to do it with a shared pointer, but probably in the end the work is going to be a shared pointer. But I haven't discussed this completely yet, how I want to implement this. Now, if we have worked, we can continue on, which basically means checking conditions again and re-entering the loop. If we can't get work, so if this fiber by no means can get work because there's no more work to do, well, now we need to maybe switch to a different fiber because the other fiber can have work. This is done by the fiber switch no work. This is the switch condition if a fiber has no work. If it switched successfully, well, continue on. Maybe we have now work. Because if the switch no work returns, it means that this fiber was activated, which is gonna be a good condition that this fiber shall now work, which is why we get to continue, go up, probably have some work, go down, execute the work. So what is switch no work gonna do? Let's see, switch no work is down here. So how does that work? So basically what I'm trying to do is I'm trying to seek a next fiber. Basically I'm taking a look at my fiber queue, and if it's not empty, I am gonna get a fiber from the front into my next fiber slot, and I know, all right, there's a different fiber that I can use to put some work on. Now down here, if we have a fiber, we are now going to activate the fiber. Now, how does that work? First of all, we need to take care that the current fiber will put us back in the pool. Because currently we had no work. We were not able to get work. However, we were able to find another fiber that has work. Since we don't now have work, we can get back to the pool. This fiber shall now, as long as there's no new work on the job system, should be put it on the pool and stay on the pool. So I'm basically telling this fiber now goes to the pool. This one is reserved for later usage. And this has been done by this CB fiber return to pool activator callback. So this is the next fiber. We are basically telling this fiber that it shall call that callback with our current context as soon as it starts working. And it will start working when we are calling the thread switch to fiber for the next fiber. Now, depending on where the next fiber is, it will be in a completely different code block. The next fiber could be on that exact line and then continue on here, but it could also be somewhere down here because there's also a switch to fiber. The other fiber could also have executed that switch, so it can also go in here. But you can already see after every thread switch to fiber, we have a fiber reactivate exec. Always. It's always going to be there. Every call that you're going to see for a fiber, every time I switch to a fiber, we're going to have a reactivate. It's not going to happen otherwise. We're always going to have a reactivation or after the or an execution of the reactivation after a fiber has been switched. There's only one condition where it's not going to be directly under it. And this is the one condition when the fiber starts the first time and runs through the whole loop of like iterating through all of these fiber main functions until it hits the fiber call function, which sets it up on its own. But then, as you can see, well, we also have a fiber reactivate exec call, and this is why it is here. Because every fiber, as soon as it starts operating, needs to check if it needs to do some reactivation on a different fiber. What is that reactivation going to do? Well, actually, the call is very, very simple. I think it's up here. So basically, what it's going to check if it has a activator in its own context. So this is now the new fiber. Do I have an activator that I shall execute for a different fiber? If yes, call this activator with the current context and the previous context that's stored in my context, and after I have called that, set the activator to null pointer because the activator has executed. So fiber, reactivate, execute. Very simple operation. It's just calling this activator and setting it to null pointer. Now, basically what happens after the reactivation of the fiber has been done, if we had no work, where is my switch no work? Basically what happens is we are returning true, and this basically now means switch to fiber. We are now on a completely different condition. Now basically switch to fiber, as I told you, is now completely switching the context. Now let's not care about what the other fiber, the next fiber that we have switched to, has done. However, at some point, thread switch to fiber returns, which means that the old fiber gets activated again. This then also needs to clean up work on the fiber that has activated itself, and then it returns true. And basically, well, if it returns true, we're going to jump back up here into my fiber call. And basically, it means that we're going to go to the continue statement, which we have already discussed. If this function returns false, because there is no work, we are basically going to sleep. We are sleeping for 250 nanoseconds. I don't want to overload the CPU. This is maybe at some point also going to be, or probably at some point, not going to be a magic number and being replaced by a configurable value. But what's going to happen is that we are going to sleep for a certain amount of time to kind of like not put load on the CPU. Because if this line isn't in here, even if we would yield to the operating system or the task manager, you would have spikes to 100 on that core that's executing because it's basically just very fastly going through the loop and it doesn't have work, it doesn't have work, it doesn't have work. This is like a trade-off. On a game engine, this would probably not be a good idea. Or maybe it would be a good idea if there's no work, but on a game engine, this could introduce lags. On the game engine, if you have something like there, like 250 nanoseconds are not too bad. It's fast enough for a game engine to react, but if you were to put like something like 1 second in here, this would be a lag, potentially, because then the job is enqueued on the fiber is still asleep, and it would give you it could give you a second lag, because the job is delayed by a second, because the thread is awaiting. Just something to be cautious for a web server, and this is not a crucial time. Basically, I've upped the time until I see that the task manager is no longer spiking. This is purely experimental. So yeah. and then it continues running. And this is basically how a fiber will always work. At some point, a fiber, of course, has all of these conditions met, and it's no longer met, which means that it is in shutdown, and as soon as it is shut down, it will say goodbye. This one is something that I can delete now, because this already checked that there's no work. This was something that I have for debugging in there, then I added a condition here and fixed the bug. So yeah, then I had like the goodbye from fiber. So yeah, now what happens down here is something really interesting. It's actually this is a infinite loop for all normal fibers. A normal fiber that's not a root fiber will never go out of this loop. So a normal fiber will always, which just basically means is root fiber is false, so this will always be true. It will always be in here. A normal fiber at that point will always call this switch find root. So it will switch to another fiber in seek of finding the root. This will always happen. Another thing that is indicating that even if we are a root thread, as soon as the IDs doesn't match, so my root thread ID and the current thread IDs don't match, no, we're gonna start switching. So basically this is deprecated, this comments, deprecated. This comment needs to be like, this is why you normally don't like putting comments in code these days, because it's gonna rot. This condition has been introduced later and I haven't updated the comments, which is not good. So yeah, basically what will happen is it will always switch fibers. Every time a fiber encounters this curl block, no matter if it has been reactivated or it's the first time it calls that, it will basically see that it's not a root fiber or that it is a root fiber with the wrong thread ID in the current context. So it will basically switch to find the root. As soon as it is a root fiber, it can return. So how does that switch find root work? Let's take a look. So let's go a bit down to find the code block. There it is. So how does that work? So basically, if we are finding the root fiber, this means that we have no more fibers in the pool. So what we basically can do is we can only take a look at the fibers and not in the pool. We have no in the queue, but we have all in the pool, or if not, they will at some point go in the pool. So basically what we need to do is we're iterating over the pool. So what we are doing is next fiber equals fibers, next fiber. So we're getting the next fiber from the pool. And if we got the fiber from the pool, we can now basically go in and reactivate inject again. Now reactivating to put it back to the pool. And then we are switching the context, and then we are executing again the reactivation. So reactivation inject and execute the same as we are using it previously. And a simple normal switch. Actually, I even have a critical log, so it can actually not happen that we have no more fibers in the pool. I don't think that's actually too bad, because it might not be that all yes, it is that all fibers. Of course it's all fibers, because only if the queue is empty and only if the task list is empty and only if these two conditions need to be met, that any fiber can escape. So it's actually okay to log this critical. I don't know why there's no message. Let's copy the function name. Fiber switch find root failed. This, if you see this, my great respect on breaking the task system. Let's write it like that. That's a nice comment that people like, and later on, if they really see it, they gotta really laugh about it. Or maybe not if it's a productive application, which simply at some point closes and throws this critical log message. But yeah, basically that's what happens, right? And this basically just keeps idling through all. Basically what this is doing, it's iterating through all fibers in the pool until it finds its good match, and then it returns, and everything can be converted back on the threads stack. That's exactly what we are trying to do. Now, this is actually everything from the job system, but there are still more functions. Why are there more functions? Well, because of scheduled task, we don't need to look at this. But the very important function that is in here is the so-called fiber stall. The fiber stall function is called by a fiber when it encounters a blocking condition. So we have async polling IO, for example, or SEO, or like any like call that would normally block. We ask kind of like a, would you block? The call says, yes, I would block. Okay, call fiber stall and try at some point again. So fiber stall somehow called in a loop. For example, on a lock that needs to get acquired as well. So fiber stall is now the interesting function because this is now actually being called completely out of context somewhere along a call stack. And if I find my fiber stall, I'm not sure why I can't at some point find these. Fiber stall, there it is. Basically what I'm going to do is I am retrieving the fiber. If I am running on a fiber, I do stuff. If I don't run, I do nothing. Now the next thing that I am trying to do is first I get the fiber context, and then what I'm going to try is to try a fiber switch stall direct enqueue. Now this is a very long word for a very simple thing. This is a fiber switch which directly enqueues the current fiber. So instead of putting it back to the pool, it uses a different callback to enqueue. So if we are scrolling up, we have it here. It works completely the same. It is getting a fiber, it is switching, it works the same than what we had previously, but instead of the no-work function, which returned to the pool, we are now have the CB fiber re-enqueue function. I think we haven't talked about these at all, but basically what they do, one of them is putting it in the pool, which is locked itself. The other one is pushing it in the fiber queue, which is locked by this fiber queue lock. So yeah, one of them re-enqueues, one of them returns to the pool. It's really a really simple one. If this doesn't work, if we cannot execute a fiber switch with a direct enqueue, which means that there are no more fibers left in the queue. Actually, I think this is even using the queue. The other one was using the pool to cut a new fiber and fiber queue. It's both from the fiber queue. No work is queue, and the other one is also from the queue. Yeah, it makes sense. It might not make sense. Does it make? Yes, it makes sense. Right, it makes sense. Does it make sense? Yes, it makes sense. I'm sometimes confused of the system on my own. Sorry about that. It makes sense because the if it's called from the fiber's main loop, then the fiber can supply itself with work, so it does not need to take one from the pool. It just checks if there's something in the queue. If there is something in the queue, it takes the one from the queue. Otherwise, it supplies itself with the work. This function cannot supply itself with work because it's a stale fiber. If it is a stale fiber, it means that it still has some work, so it cannot swap its own work. So it has two options. Either it's getting something from the queue, and if it does not get something from the queue, it needs to dispatch a new fiber that can run on the current execution context. So we are trying to get a new work and a new fiber. Next one. And first of all, what I'm trying to do is I'm trying to get work. If I get work, it's simple, right? I'm trying to get the next fiber. If I have work and no next fiber, bad things happen. Put the work back because we don't have a fiber for the work. If we don't have a fiber for the work, we are now pushing to the front. We are popping from the front, so we are pushing from the front. So basically, we're getting a work set. If the work set succeeded, but the fiber failed, we are putting it back in the front of the queue so that we don't have like a re-enqueue of the work, which could lead to some bad scheduling. Really bad scheduling, because of course they should maintain the order. There might be some other tasks that had already slipped through, or maybe multiple tasks that has been slipped through, but it's not as bad as pushing it in the back. So that's basically what happens. Else, if the next work is successful, so we have work and we have a fiber, if this is the case, we first need to place the work on the fiber. So we are getting the context from the fiber and we are putting the work in the work slot of the fiber. And then what we can do is we can enqueue the fiber. So basically we are not directly switching to that fiber. We could do it, but we are actually not doing it in here. But what we are otherwise doing is we are basically putting it in the fiber queue, because if some other work has now reached the queue, it really doesn't matter. We are putting it on the queue, and then we are again trying a fiber switch stale direct enqueue. If it succeeds, it's good. If it fails, we yield. It could actually fail because our work could have already been stolen. It's okay. We can continue on. So we are yielding here. And then there's another yield condition down here, but that's a different one. That's basically if this one actually, why is this one here? This is not a good idea. Next work but no fiber. We can put the yield in here. That makes it a bit more streamlined. No, not in here. Huh? Nah. No. Definitely 2 times the wrong location in here. No, because, okay, because here is, let's make it like this so that the critical section is not too long. Because if we are yielding in a critical section, it's probably a bad idea. All right, so this is basically how the job system works. And in the end, it currently doesn't look very unspectacular for what it is. It's probably going to change over time, and the video is way too long, but this is a complicated system. So I hope this one has brought you benefit. And you can even like see the out of order execution, like 6562 8190. Like it's completely out of context. It's all around here. And you can see that we have a nice logging issue. I don't know, but I don't get the custom flex of SPD log working currently. Actually, I wanted to show a fiber ID, and I also want to in the future show a task ID. This should already work with the fiber ID. The task ID should be just a single bash. I can't tell you why SPD log is not calling my custom formatter. It's looking exactly how it looks on the docs. ChatGPT does also not know on how to tackle this, even though ChatGPT recently screwed me more up than it helped me, especially with like stuff like talking about creating our programming languages and stuff like that. And yes, I am currently working on creating an own programming language, but it's a language that you're not going to use in your daily programming work. This is already what I can tell you, but this is a big thing that I'm dropping now in the end of such a video. I have quite a big project that you're probably going to hear nothing about on YouTube. Really nothing, because this is crucial for me financially and also for everything. But I'm working on a big thing. You might hear it that one, but probably not this year. I hope that I get a rough working at the end of this year. Like I have this web server now that needs to get done. This is now occupying me at least like at least this web server is going to cost me like full attention until like probably mid to end of February. So it's going to be full attention for the web server. Then I hope I can jump to the new project mainly and only work on the web server if I need. It's probably not going to work, so the web server is probably again going to cost me 1 more month, which is already a fourth of the year on the web server. But I hope that for this year I can then tackle the different project. I do have invested a high amount of money already in the project. Which seems interesting, but it's already telling quite a lot if I tell you that I've invested money. I'm not going to tell you anything. Like it could be already obvious, but it's not. Yeah. So basically, if I press Ctrl+C, this is also something that I've implemented now. Goodbye, hello, goodbye. You can actually see that we are getting a lot of hello and goodbye, which actually are all currently debug messages, but should probably more be trace message. This is something that we might should change, because it's doing a lot of hello and goodbye nowadays, because it's like screwing around a lot. Like, let's make these traces. But actually, no, let's keep them at debug. They are at start and shutdown. At the end, they will only be there if you're really trying to debug the application, right? Debug messages will be in a release build, but only on verbose logging, so it might be interesting if you're definitely seeing when tasks start and stop. But yeah, in the end, you're going to get goodbyes from everything. So that's a good idea, like goodbye from threads, and every fiber is going to say goodbye to you, and they can actually see that the activation of fibers work. Actually, it's more interesting to see all the fiber hellos, because it actually shows you how many fibers are really active. The other ones are just later on iterated through. But actually, if you're taking a look at how many fibers are active, you can see like 1, 2, 3, 4, 5, 6 fibers are running on like 4 worker threads for this example. And actually they are only running because I haven't really shown you the test case, right? The test case currently is just a simple say hello, why not task that has a constructor that nobody needs anymore, and that has a size t of I, has a fiber schedule and has a done flag. Then it runs and it just basically tells a lot just to force fiber context switches to see that they work. And then it says hello, and then it sets done to true, and then it's also checked that the task has been done, because I managed to leak tasks. It was a quite interesting thing, but basically what I forgot was I forgot to, down here in the fiber stall, I forgot that. No. I I forgot that one. I forgot setting the work to the fiber, which of course meant that it would get itself some new work. So every fiber context switch was a loss of work, which was not good. But yeah, that's it. Long video. Thank you for watching. See you in the next video. Make sure to like and subscribe and have a nice day.